All right. Good evening. Um, Thanks, Krishna, for joining. So, I welcome you all for my fifth problem-solving session of this course, Aeroengine gas turbine cycles. In this week, what we are going to see is about turbofan engine, its classification and constructions of turbofan engines. Um, Also, we will be performing a calculation for a forward fan unmixed single spool turbofan engine, and also we will look at its performance. Okay, so actually this is what has been covered in the week 5 lectures, and I hope you all have gone through the week 5 lectures. And yeah, so I will be having one question with me for this turbofan engine, and then I will be showing how to solve and what are the equations need to be considered, and I will also be giving you physical insights in between. Okay. Before we start, there are a few important announcements I want to make. It's the same announcement that I made last week also. Please register for your exam. Um, it is uh, it is important that you know check your capabilities and learning, basically your learning capabilities. The reason why I say is the courses like this requires uh, additional uh, you know the additional considerations, additional time you have to spend for this course. Until you don't register, you will not have the uh, willingness to spend that time. And also, um, just by sitting in the lectures, just by watching the lectures, you will not be gaining anything. And since this course is also more problem oriented, and it gives us more, it's a little advanced course. Until you don't register, until you don't practice the questions, until you don't practice the contents that has been taught in the course, until and unless you do this, you will not be able to gain mastery in this subject. So and also registering for an exam will make you will actually gauge you like how smart and intelligent you are in grasping the concepts. And so we strongly recommend you to register for the exam. And also, as I already told, if you get an you will get an opportunity to do an internship with Professor Chetan Mistry at IIT Kharagpur. Okay. And yeah, so whenever you have doubts, please use the common forum to ask those doubts. And also you can come and ask to me. It's better you do both of them so that it will be helpful for other students who are not attending the sessions. They might be also will be helpful for the will get helpful uh, based on your doubts. Okay. Um, with these announcements, let's just directly jump into the this week contents. Uh, So we all know we studied turbofan engine in this week, and the turbofan engine, basically the difference between turbojet and turbofan is we have additional fan component attached in front of the compressor, and you have two pathways for air to flow. One is a core flow in which basically it goes through compressor, combustor, turbine, and then exits via nozzle. The other is the fan flow, or you can say bypass flow, where the flow gets diverted from the compressor, flow gets diverted from the core flow and just goes through via fan, and it gets expanded in the nozzle, and that is also give you a thrust. So basically thrust will be produced in two different sections. One is the core flow and one is the bypass flow. And this is, we say, unmixed flow because the core flow or core stream and the bypass stream will not mix. Okay, the core stream will exit as a separate stream, and the bypass stream exits as a separate stream, and these two separately generates their own thrust. That's why we call it unmixed. And we say forward fan because fan is present at the front of the uh, engine, or basically front of the compressor. So there are other ways to design this. There is a aft fan engine, there is a mixed flow engine. All these things you will study in a subsequent weeks, probably week 7, 8, and 9. There is also geared turbofan engines. Probably in week 7 you'll be uh, looking at it. So but this week we just introduced the turbofan engine. We will be doing a single spool turbofan engine calculations. Let's just quickly look at the TS diagram. How does it look now? In the TS diagram, we all know the air enters at P infinity, that is air present at P infinity will get sucked in to the inlet, and the inlet here is from infinity to 2. The station number at which the inlet ends is 2, and then only it enters the fan. So until 2 there will be a um, slight increase in pressure, uh, if at all there is. Okay. And uh, across the fan is nothing but a kind of like a compressor, so it also going to increase the pressure of the air entering. So it goes from 2 to 8, where 8 is the station number at the exit of the fan. Okay. And after 8 there are two streams. One stream is going to go in the bypass, one stream is going into the core of the engine. Okay. So let's focus on the core of the engine. After it exits the fan, it enters the compressor. In the compressor you get compressed, so the pressure rises from P08 to P03, and then you have a combustor. There will be a pressure loss. We all know about this. So it goes from P03 to P04, and the temperature at 4 is the maximum temperature that you see in your aircraft engine. And after that you have compound turbine, and across the turbine there will be a pressure drop to P5, P05, and then you have a tailpipe if there is any pressure loss that happens there. And then you have nozzle where the expansion of the core flow engine will happen from 6 to 9. Now, this is what happens in the core flow. In addition, what you also have is bypass flow. So the air which enter into the bypass region from the fan has only one component at the end. The component is nozzle, right? So at the station number at the exit of the bypass flow, exit of the bypass nozzle, or you can call it fan nozzle, will be 10. So it has to expand from 8 to 10 basically. Okay, 10 is the exit of the nozzle. So that is why you have this additional. So you can see this, you have this additional line which is from 8 to 10. Okay. So this is will be your typical TS diagram for a real turbofan engine, single spool real turbofan engine. Now let's go ahead and do something different. um, yeah, before that we'll look at the classifications. This we all know, turbofan engines, it can be either forward fan or aft fan. As I said, if the fan is present in the front of the compressor, it's a forward fan. If the fan is present in the rear of your engine, then it's aft fan. We'll come to that, what is that and how it works. And in a forward fan you have mixed flow and unmixed flow. As I said, this bypass stream and core stream will not mix. If it not mix, it's a mixed flow. If it mixes, it becomes a if sorry I said the opposite. If it doesn't mix, then it becomes unmixed flow. If it mixes, then it becomes a mixed flow, which means a core stream also will come, and bypass stream also will come. At the exit of the nozzle you will have a you will have mixing of these two streams, and then it exits a different nozzle. Okay, that is how it works. um, that is the mixed flow. And then in the mixed flow, what you also have, since it mixes, after that you can have a afterburner. So that is why it can either have afterburner or you cannot have. So there those that is the two calculations that you have. And turbofan engines basically it can be high bypass ratio or low bypass ratio, but the margin is usually bypass ratio low means like 2 3, and high means like 10 15 16, something like that. Again, here also you can have afterburner, non afterburner. And then similarly you can in the forward fan you can also have additional classification as single spool, two spool and three spool. And all these single spool, two spool and three spool have its own classification. For example, if when you say two spool, whether a spool should it be in the should it be connecting low pressure compressor to low pressure turbine? Should it be or the low pressure turbine should only be connected to the fan? All these combinations will come into picture. Uh, on top of this combination you can also have geared combination. So that's the whole classification of turbofan engines. um, it's a different things they added in order to achieve something. Okay, so you just need to understand why we need to add such a component, and why what is it going to give us, how useful is that to us. That is the thing you need to understand. If you understand that, you'll be able to easily uh, come up with your own designs, come up with your own new technologies to model this, to design this kinds of turbofan engines. Okay. Um, all right. Uh, we have one question from Tusha. So, what is dry combustion in aero engine? Um, Dry combustion. Um, so, Tusha, could you be more specific? What is that you are asking? Dry combustion.
Sir, now I saw before this meeting that the Kaveri Indian are doing dry combustion with higher efficiency over there in Kaveri engine.
Okay. Okay.
Okay, so there, to I didn't understand what is dry combustion means. Can
Right.
get
Right.
it?
Right. Okay. Um, Yeah, probably I may need to also look into it. Um, I also remember such. We will maybe let's get back to this question at the end of this discussion.
Yes.
Okay.
Yes,
Okay.
sir, yes.
All right. So we'll complete this question, and then we'll get back to this question again. Okay. Um, so in the turbofan engine, let's say all this. So in the last slide, we saw a TS diagram, which we saw it to be a real process. Now, let's say if you assume isentropic process, how does a TS diagram look? That is the first question I'm uh, posing you guys. So this is your TS diagram, and initially you have P infinity. Let's say if it's an isentropic process, like every process uh, in your engine is an isentropic process, except the combustion chamber. Combustion chamber, of course, will not be isentropic because we are adding fuel and combustion is happening, and combustion is not an isentropic process. Um, okay, so uh, by the way, I hope everyone understands what is isentropic process. Isentropic process is nothing but a reversible adiabatic process where entropy doesn't change. So that is your first clue in order to draw a turbofan engine TS diagram with for an isentropic process. Okay, so from infinity to 2 we have a diffuser, and in the diffuser, when you say isentropic, what is going to happen in the diffuser? Pressure is going to rise, and so its temperature. So, but it's an isentropic process. So, what you will actually have is a vertical line. Okay, so the entropy will not change. So, entropy will be remaining constant. Okay, so when when you are given a question and asked to assume an isentropic process, when you draw a TS diagram, please make sure that you don't make this mistake. It will be a vertical line, so there won't be any change in entropy. Okay, from and the next component is fan from 2 to 8. So for 2 to 8, again, there's going to be some compression happens, pressure is going to rise, temperature is going to rise, and hence you will end up having again a straight line because it's an isentropic process. So every process inside this engine is an isentropic process. That's the assumption that we are taking for now. Okay, now if I continue and let's say I focus on the core flow. Okay, in the compressor, again what you have an increase in pressure, but it's an isentropic, so you will again have a straight line from 8 to 3, and 3 is the exit of the compressor, and the gases enters the combustion chamber. And we know that combustion chamber is not an isentropic process, um, because the gases are reacting and entropy changes, and hence it's actually a constant pressure heat addition process. So it's basically a heat addition. uh, and we are going to assume that combustion chamber doesn't have any pressure losses. So if that is the case, you have this line P03 to P03 line, or isobaric line in a TS diagram. So during the combustion process, if there is no pressure loss, what would happen? The process lies in the same line. Okay, so I hope everyone is able to understand. So it will process will happen only along this line. So that's why you will have the exit of the combustion chamber. Since there is no pressure loss, it follows the same line and it reaches 4. But the point 4 is at higher temperature. That's why you see the point 4 has higher temperature than the T4 is greater than T3. Okay. um, yeah, and then you have turbine, which is also isentropic, so you will have a reduction in pressure and temperature. And then you have jet pipe, which we are assuming there's no change in pressure. This is an ideal turbofan engine. This is how it looks. And then we also have nozzle, where the expansion is also going to be happening, and that also we are assuming isentropic process. Expansion also can happen at isentropic process. So you will have 6 to 9 as a straight line. So this is how this looks. A turbofan engine, if it's an isentropic process, it will be a straight line going up, and an isentropic constant pressure heat addition, and then isentropic expansion in turbine and nozzle. Okay. Now the question is this for ground condition, or is this for flight condition? So whatever we discuss, can you guys guess whether this is for ground condition or flight condition? Any idea? By the way, you guys no need to have any stress that you should give only right answers. There is no right or wrong answer. Uh, it's just to test your understanding. You feel free to give your answers or type in your answers in the chat box. All right. Okay, you guys are thinking too much. Let me itself give you answer. So this is for a flight condition. Okay. So the reason is, if it's in ground condition, the Mach number is 0, and the Mach number of the flight is 0, or the air which enters will have uh, a 0 Mach number, right? So there won't be any pressure rise in the diffuser from infinity to 2. Okay. And hence this but if you're flying, the air enters at, let's say, Mach number zero point 0.8 or zero point 0.9. So there will be a pressure rise as it enters and in the diffuser. Okay. So that is the reason you will have infinity to 2, there is a pressure rise, and hence it will be in the flight condition. So that comes to the next question. So if it's a ground condition, what is going to happen? As I said, the infinity to 2 will not be there. Instead, you will have, if it's in the ground condition, the green line over here corresponds to atmospheric pressure. And at atmospheric pressure, or when m naught is equal to 0, the green line is the pressure. So all your process starts from this green line. Okay. So from here, from 0 to 2, you will have some pressure rise, and then 2 to 8 you have fan, and then you have 8 to 3 you have compressor. This is a core flow, and then you have a combustor, and then you will have turbine and nozzle. So this is the only change. Your pressure rise will start from 2. Okay. So that is something, please note. If not, it starts from infinity. So if it's in the flight condition, the pressure rise starts from infinity. If it's in the ground condition, starts from 2. Okay. All right. I hope it's clear. Now, let's say if I say for the same thing, let's say it's in flight condition, and this is your TS diagram, isentropic process. If the compressor pressure ratio P03 by P08, okay, which is nothing but across the compressor, what is the pressure ratio? P03 by P08. If it is increased, keeping that T04 is constant. So I am telling I am keeping T04 to be constant. Okay, which means I'm not changing the maximum temperature or turbine entry temperature, but I'm just increasing the pressure ratio of the compressor. Okay, which means P03 by P08, let's say it was some value, I'm increasing it a little bit. Now, what would happen? So if I want to draw a TS diagram, again from 0 to infinity to 2, you will have a pressure rise. Across the fan, you will have another pressure rise. And from 8 to 3 dash, now let's say it's a P dash, P dash 03, I'm referring it as P dash 03, which is higher than P03. Okay. Uh, then what would happen? Now I cannot change the turbine entry temperature because that's a design parameter. You cannot arbitrarily change the turbine entry temperature. So what happens is you will be adding only less amount of fuel to reach T04. Okay, and because of that, what would happen? The area under this curve will change. So that will be very clear. So after this the red line, if you follow, after T04, the turbine expansion will happen. That will expand to a certain uh, pressure, and then it goes through the nozzle. Again, it will expand to a certain pressure. So if you see the area under the curve of black and area under the curve of red, that will be changing a bit. Okay, and these things will lead to your change in work done by your cycle and change in your thrust and efficiencies, all those things it will change. uh, uh, and I urge you to think about it. What are the things it will change? So these things we already discussed in the lecture, but I just want to quick give a little nudge uh, towards the importance of this concept. Okay, all right. Let's go ahead and solve this problem. It's a simple problem. It's a simple turbofan engine problem. But here we are going to assume isentropic process. In your lectures, you have already assumed it as a real turbofan engine, and you have solved enough number of problems. Uh, so here I'm going to assume it as an isentropic, and we will try to solve this problem and see where it goes. Okay. So here you are asked to calculate the specific thrust and fuel to air ratio, assuming that all the processes are isentropic, as we said. The flight Mach number is zero point 0.8. Flying altitude is 34,000 feet, where the ambient pressure and temperature is given. So ideally, this altitude will be of no use for us in calculation. Sometimes what people do is they will just give you altitude, and you may need to find the ambient pressure and temperature. That's why every time when we ask question, we include the altitude. Um, so here altitude is also given, pressure and temperature also given, so there's no problem. And the fan pressure ratio is 1.5, compressor pressure ratio is 6, bypass ratio is 1, lowest fuel eating value is 45,000 kilojoules per kg. uh, Here we say lowest fuel eating value. uh, can you guys guess what it means? So the lowest fuel eating value actually refers to the there are two heating values, lower and higher, right? The lower heating value corresponds to the, you know, this we already addressed in the previous sessions also. Lower heating value corresponds to the real heating value, where once you combust it, if you don't allow the H2O present in the or moisture present in the product gases to condense, the temperature or the heat that heat release that you got is the lower heating value. And if you allow the H2O to condense, since it condenses, it releases some more heat. And when it releases some more heat, if you add that heat to this, then it becomes a higher heating value. Okay, that's the two difference between these two things. And then you have specific heats of air and gases. You have maximum cycle temperature. Or maximum cycle temperature here is nothing but turbine entry temperature. So all right, this is the given parameters. I've already made it here to make it quick, process of solving. And then we have efficiencies and losses. uh, But here the efficiency is 100%, all the efficiencies, which means isentropic process, and the losses are not present, which means the pressure losses across the burner is lost present, and also tailpipe is not present. And then we have gamma C, gamma H, we are assuming it to be same 1.4. What we need to find is specific thrust and fuel to air ratio. Okay, these are the two things we need to find. Now let's see what is the process in which we need to find. We have inlet condition, we have given inlet condition, we have also given Mach number at the inlet, which translates to velocity of the air stream at the inlet. uh, and then since once it goes through the inlet, there will be a pressure rise, we can find P02 and T02, and after that it has to go through a fan. Okay, please remember that. So after inlet there is fan, and after fan only these two streams divide. Okay, so that is something you need to note. So across the fan there will be a increase in pressure, and then you have that pressure ratio is 1.5, and then you have a core flow, and in the core flow, one second. Okay, in the core flow what you have is compressor, and you have certain compressor pressure ratio which is 6, and then you have a combustor where you are adding some fuel, which from which you can find, based on energy balance, you can find fuel air ratio. And from combustor you can have turbine, you will have turbine, and turbine, across turbine there will be a pressure reduction which gives work, which drives the compressor and also fan. Here it's not very straightforward, but it drives both compressor and fan. Okay, it's a single spool turbofan uh, configuration. So when you do energy balance for turbine, you have to include both compressor and fan. Okay, and you have tailpipe where there is no losses, and then you have a nozzle which is in the core flow, and since it's a unmixed flow, these nozzles will be separate. And from nozzle you will get P9, T9 and V9, which will use it for thrust calculations. In the bypass flow, what you have is you have nothing but once the air gets compressed by the fan, it gets expanded by the nozzle. That's all it happens. Okay. um, and in the nozzle you will have from the nozzle the exit will be P9, actually it should be P10, V10 and T10. There is some uh, typo here, I will update it when I upload this. Okay, so from nozzle you will get a separate set of quantities, P10, T10 and V10. From there you can find thrust from the bypass stream. Okay, let's go and solve this problem. So first, initially you have inlet, um, and inlet Mach number is given 0.8. So we know this isentropic flow relations, T naught T02 by T infinity, which is 1 plus gamma minus 1 by C m infinity squared. So if you substitute these numbers over here, T infinity is 220 Kelvin and m infinity is 0.8, you will be able to get T02, and the T02 would look something like 248.16 Kelvin. Okay. Um, Similarly, what you can do, you can find the pressure. So pressure, again, this is also coming from isentropic flow relations. So if you substitute these numbers over here, these are, every day you are seeing, by now you are master in this, uh, component wise finding the station quantities. I hope I think you guys are master in this. So I'm just going forward with this. So let's not waste time much on this. So across infinity to 2 there is a pressure rise, and this pressure rise would be something like 37.682 kilopascal. So from 24.72 kilopascal it has increased to 37.682 kilopascal. Right now, after inlet what do you have is fan. Okay, so in the fan you have a pressure rise of 1.5. Okay, the pressure ratio across the fan uh, is 1.5, and the inlet to this is 248.16 Kelvin temperature and 37.682 kilopascal. Now since we know the pressure ratio is 1.5, from there we can actually directly calculate the P08. If you calculate this, what would happen? So it will be just 1.5 times 37.682, which will come out around 56.52 kilopascal. Probably you guys may need to check my numbers. I might have made some arithmetic mistakes. Okay. Now you can also find temperature. Okay. So how do you find temperature? We all know this is also nothing but from the isentropic process. So we know it's a basic thermodynamics you know formula, right? Isentropic process. If the pressure ratio, we know the pressure ratio, then we can easily find the temperature ratio. So if you substitute the pi fan here is nothing but P08 by T08, and if you substitute those numbers here over here, 1.5 power 1.4 minus 1 by 1.4, you will end up having temperature ratio of 1.1228. Okay, and um, since we know T02, we can also find T08, and if you substitute these numbers, you will end up something like 278.64. So the pressure and temperature with which the air enters the or leaves the fan is this much. P08 is 56.522 Kelvin kilopascal, and T08 is 278.64 Kelvin. Now you must remember, if the fan is not there, it would be entering at much lower pressure. Okay, it will be entering at lower pressure and lower temperature. Okay, so that is something you should know. And now we will try to calculate all the station properties for the core flow. In the core flow, what you have is first component that you encounter is compressor, and compressor has a pressure ratio of 6. That's for this case. And again, since we know the pressure ratio, we can directly find the pressure at the exit of the compressor. So it goes from 56.52 kilopascal to 339.13 kilopascal, which is like 3.39 bars. Okay, 3.39 bar is the pressure at the exit of the compressor. This would be your highest pressure in your whole uh, engine. Okay, and similarly, again, the relation is very simple. Similarly, you can find the temperature also, T03 by T08. And if you substitute these values, you will end up having uh, higher temperature, which is around 464.9 Kelvin. Okay. Now, the next component that you have is combustion chamber, and across the combustion chamber, actually, there's no efficiency. For some reason, here it is coming. Uh, it's a error. I will remove that burner. So, um, yeah, it enters at 339.13 kilopascal and temperature 464.9 Kelvin. And the T04 at the exit of the compressor is, sorry, combustor is 1500 Kelvin. So we need to heat up your air from 464.9 Kelvin or 465 Kelvin to 1500 Kelvin, which is like more than 1050 Kelvin difference. Okay, since there are no losses, P04 will be equal to P03, and you must do energy balance. And here you need to be a little careful. The energy balance is between the core mass flow rate. Okay, so the mass flow rate of the core, which enters at T03, plus the mass flow rate of the fuel times QR, will be the mass flow rate will be equal to uh, mass flow rate of core plus mass flow rate of the fuel. Here F is fuel, not the fan, so please be careful. Mass flow core plus m dot F times Cph times T04. Okay, so this is purely the core flow. So the mass flow rate of fan never came into the picture. So sometimes what people do is they will give you m dot infinity, which is the entire mass flow rate to your engine. Okay, in that only part of the mass flow rate is going through the core. So when you do this energy balance, you cannot put m dot infinity. Till now we use turbojet, so we just use put m dot infinity. But in turbofan engine, you should be a little careful. What is the mass flow rate entering? What is the temperature with which it is entering? You should be careful. Okay, so make sure you write the proper energy balance that you have here. Okay, and if you rearrange it, you can find F, fuel to air ratio, and here the fuel to air ratio is based on the core. Okay, mass flow rate of the core. So if you continue doing this calculation, you will end up having fuel to air ratio to be 0.02899. Okay. All right. Um, the next component that you have is turbine. In the turbine, uh, across the turbine, there's going to be so turbine is nothing but a it's going to extract energy from the flow gases, and it is going to use it to drive the compressor and also fan in this case. Okay, so it's a single spool turbofan engine, so it is going to drive both fan and the compressor. Now if you do energy balance for this turbine, so across the turbine you have some energy change. Okay, this energy balance is not same as combustion chamber energy balance, so please be careful. This is about how much energy turbine has extracted, and that energy should be equal to the how much energy the compressor and fan requires. Okay, please note that. So the how much the amount of energy extracted from the turbine is, if you it's a the this would be m dot core plus times 1 plus f. The reason is f is the fuel to air ratio, m dot f by m dot core, and it's nothing but m dot core plus m dot f, which is entering the turbine, and when it goes through the turbine it changes its temperature from T04 to T05. So that is what you see here, m dot core 1 plus f into uh, uh, T04 minus T05. This is your turbine uh, work extractor, okay, from the gases. Now this should be equal to m dot core, so times CPC of T03 minus T08. What is T03 and T08? So it is nothing but the compressor. Here if you see, this is the compressor that you have. Across the compressor there is a pressure change and it requires work, and that is given by the turbine. So that is the first term over here. And the second term is across the fan. It also requires work to rotate the fan. And across the fan, what is the temperature change? You have 8 to 2. So that's what you see here, T08 minus T02. Okay, and but the mass flow rate here would be a little different, m dot core plus m dot fan. So because the entire flow which enters is m dot infinity, which is nothing but equal to m dot core plus m dot fan, and uh, that is why you need to add both of these mass flow rates, because fan equally pressurizes both of these mass flow rate. Or in other words, after fan only you will have two different streams. Until then it's a single stream. Okay. All right. If there are any questions, doubts, or confusions, please stop me at any time and ask questions. So if you just rearrange this, you will end up having this equation. I'm sure that you have already seen this equation in the lectures itself. It shouldn't be a surprise for you. Now, if you substitute these numbers, you will end up having something like, if you multiply T04 also to it, you will end up having T05 as 1289.6 Kelvin. Okay, so the temperature has reduced from how much, 1500 Kelvin to 1289 Kelvin. Okay, this is the turbine energy balance. So this is the only difference from turbojet to turbofan. Only thing is you have additional fan component, your energy balance in your combustion chamber, and turbine changes. That's it. And the next is we also need to find the pressure, how much pressure has reduced, and for that we are going to again use it, since it's an isentropic process, we can still use the same relation. And if you do the same relation, your reduction in pressure would be 199.82 kilopascal. Okay, which is like 1.99 bar, 2 bar. So from 3.39 bar it reduced to 2 bar. And after that what you have is tailpipe, which doesn't have any losses, so your P06 and T06 will be same. Okay, and the last component that you have is nozzle, and in the nozzle it is going to expand and reaches some certain velocity. So one thing you need to notice, till now we use P06, T06, there is a subscript 0, but when it comes to nozzle we don't use 0, because All this P06 and T06 are stagnation properties. They are not the real pressures, static pressures and temperatures that you see at the exit of any station. Okay. But what you are interested in is the absolute static value of your pressure and velocity at the exit, which will be used to calculate the thrust. So that's why across the nozzle we will find at the end we need to find static property. We don't need static property at any station, but at least at the end of the nozzle we need the static property in order to get our performance parameters. All right. Um, So as usual, we need to first find whether the nozzle is chocked or not. And for that you have, since this is an isentropic process, you have a simple equation. And if you substitute those gamma values over here, you will end up having pressure something like pressure ratio to be some 1.89. So the critical pressure would come like 105.56 kilopascal. And P infinity is 24.72 kilopascal is what is given, right? Ambient pressure. Since ambient pressure is lesser than critical pressure, the exit pressure would be same as critical pressure. So whichever is higher, that will be the exit pressure of the nozzle. If the ambient pressure is higher, the ambient pressure would be the exit pressure of the nozzle. If the critical pressure is higher, that would be the exit pressure of the nozzle. Okay, so you can quickly remember like this. But I hope you understand the physical reason why we take PC to be, why we take P9 to be PC when it is higher, or why we take P9 to be equal to P infinity when atmospheric pressure is higher. So if you are in doubt of that, you can let me know. I can explain you further. Okay. Um, Going forward, we also need to find temperature, and in the temperature, again we use the simple relation, isentropic flow relation. Since the nozzle is chocked, your Mach number at the exit of your nozzle would be 1 because it's chocked, and since your Mach number at the exit is 1, your isentropic flow relation is 1 minus gamma minus 1 by 2 m square. And here m, if you put 1, you will end up having 1 plus gamma 1 minus gamma minus 1 by 2. And if you rearrange this, you will end up having gamma plus 1 by 2. So you can continue this and you can get the temperature, which will be around 1074.66 Kelvin. And once you know temperature, your exit velocity also you can know. Since your Mach number is 1, your exit velocity will be same as sonic speed. And since sonic speed is nothing but square root of gamma RT. And since R is not given, I just replaced it with Cp and gamma, which we know, right? And we can substitute these numbers and you will end up having something like velocity to be 702.49 meters per second. Okay, this is the velocity. uh, let's go forward and do the same thing for nozzle in the bypass flow. So this is one more additional calculations that you need to do from the turbojet engine. Here you will calculate P10, T10 and V10. Okay, these are all static properties, while the P08 and T08 that we have here are stagnation properties. Again, similar thing, we need to do choking condition. We need to find out, since gammas are not different, the pressure ratios will be same, but the critical pressure would be 29.86 kilopascal here. Back then it was 105.5 kilopascal. Now, even though 29.86 is still greater than P infinity, which is 24.70 kilopascal, still the nozzle is chocked even in the bypass stream, and hence your pressure at the exit would be same as your critical pressure, which is 29.89 kilopascal. Okay, and similarly you can do T80 by T08 by T10, which will be 1.2, and hence your T10 would be 232.2 Kelvin. And similarly, you can find V10, which will be same as sonic speed because the nozzle is choked, Mach number equal to 1, same arguments. And you can substitute these numbers here and you will end up having 305.52 meters per second. So one subtle thing you need to note here is, here I used CPC, but back in the previous nozzle, uh, core nozzle, I use CPH. The reason is, uh, it's a hot flow. You have gases after combustion, your CPs change and gamma change. That's why you should update your CPH for the core flow, core nozzle. But in bypass flow, there is no additional thing that you are adding. So whatever the air enters, it leaves also as a air, right? And hence you have uh, hence you use the same CP, cold flow CP. That's why you have 305.52 meters per second. And now the final part is we need to find specific thrust. We also need to find fuel to air ratio that we already found it to be 0.02899 when we did combustion chamber calculations. Now the final thing is we need to find specific thrust. For that we will write the thrust equation and then we'll try to find the specific thrust out of it. Okay. You might have noticed that in this question it never gave you they never gave you the mass flow rate of air. They just gave you the ratios, fuel to air ratio, sorry, the bypass ratio. um, yeah, only the bypass ratio they gave. They didn't really specify the absolute value of mass flow rate. Okay, so your thrust equation would look something like this: the mass flow rate of the core times 1 plus f v9 minus v infinity, which is this term is basically coming from the core flow. And then you have the pressure thrust in the core flow, and then you have a momentum thrust in the fan. Since the fan also has nozzle, and air is going to exit the nozzle with some velocity, and that velocity will be different than v infinity because fan has did some work to the air, right? If the fan is not there, whatever the flow, it's going to just go out like that, right? So the fan has did some work to the air and it is getting expanded, so it will have additional momentum when it goes out, and that also produces some thrust. It's a bypass flow thrust. And this is the pressure thrust in the bypass stream. Okay, now you need to find specific thrust. We can you know normalize it with the m dot core. Okay, so if you divide this thrust divided by m dot core, this is what your equation would look. You have this additional pressure and pressure thrust of core stream and bypass stream divided by m dot core here, bit weird. And you also have m dot fan by m dot core, which has been replaced by beta. Okay, that is what is your bypass ratio. So for now, since we don't know the absolute mass flow rate, let's just assume that this pressure thrust are not contributing, and we'll go forward and find out only the momentum specific thrust. You can say in that way, it's just a contribution from the momentum thrust. Okay, but anyway, for that we need to find v infinity, and v infinity we can find from m infinity, and m infinity we already know it's 0.8. And you can substitute these relations over here and you will end up having v infinity to be 237.9 meters per second. Okay, and what you can do is you can yeah, as I said, we'll ignore the pressure contribution, and hence you will have st, which is like only the from the momentum contribution, will be simply 1 plus f v9 minus v infinity plus beta times v10 minus v infinity. And if you substitute these numbers over here, you will end up having 553.2. The units you need to note here, it's not just randomly newtons per kg per second. It's newton per kg per second of core air, because we normalized with m dot core. So sometimes people also normalize with m dot infinity. That would be, then you need to take that also into account. It should be T by m dot core plus m dot fan. Sorry. Okay. When you do such calculation, then Newton per kg per second of air. Okay, kgs per second of air. Now here it should be core air, or the flow that is going in the core section. So we have normalized it for that. Okay, so this is the specific thrust calculation that we have here. And yeah, so this is how you solve this problem. Additional things that we took into account, the difference in solving a problem from turbojet to turbofan is we have an additional fan component. We have to uh, you know uh, apply some equations to find the station pressures and temperatures across the fan. and we need to take care of energy balances both in combustion chamber. Combustion chamber, anyway, we usually do. The change is in the turbine, the energy balance in the turbine, because the turbine here also needs to drive the fan. Okay, so that is the difference. So if you make all these appropriate changes, then also finally when you find the thrust, you need to add additional thrust contribution from the bypass string. Okay, those are the few differences that you will observe when you do calculations from turbojet to turbofan, especially for this case, which is forward fan and mixed single spool engine. Okay, going forward in upcoming weeks, we will be doing dual spool, uh, both in the lectures and also here next week. And also going forward, we'll be doing gear turbofan, and there we will address additional changes that we need to do while doing these calculations. Okay, all right. Any questions that you guys have? So as far as question is concerned, we have completed solving this. There was a few typos in my slides which I will update it, and I will upload this in the drive. You will be able to access it. Okay. Um, yeah. So if there are any questions, I'm happy to take. And if there are no questions, we will meet next week. Okay. So I have also added a few additional links over here. This is just for your curiosity. Last week I had a question that what happens if it's a bird strike? What are the things in the engine that we change? Can we overcome such things? How are we overcoming? Uh, Trying to overcome those things. Although these are not part of this course, I just added few links which would be helpful for you guys to look over if you are interested. Especially the first one, Aeroengine Safety Book. It's actually a Wikipedia or wiki page, you can say, um, where there will be different chapters. You'll be able to read chapter wise in the website itself. You don't need to download a book. It should be helpful for you guys. Okay. All right. Um, if there are any questions, please feel free to stay back and ask. I will be available in this meeting link till 9 o'clock. If there are no questions, thanks for attending. I will see you in the next class. Thanks, Krishna Kumar and Madesh. If you have any questions, please feel free to stay back and ask. I hope I'm not faster. If you want me to go a little slower, or if you want me to address certain things, I welcome your suggestions. So I think there was a problem here. It's a little difficult to edit in my iPad. Probably I will edit it in the web version.
Hello, sir. Good evening. If I may ask.
Yeah. Please go ahead. Actually, you don't need to wait till the end. You can ask me anytime. Okay, in between.
Yeah, okay, sir.
Okay,
I mean, like, I'm just a bit curious, sir. I mean,
sure.
so we are learning this course, yeah, eventually to design engine, right?
Correct.
Yeah, I mean, like, we take little steps for that. I mean, keeping that goal in my mind.
So
and drive. Yeah.
yeah, so actually this course is to um, design an engine, but from a thermodynamics perspective. Okay.
Oh yeah.
Uh,
Okay.
right. So in terms of cycle design, basically, so different components. So for example, there are different variables that you have encountered here, right? Something like you have pressure ratios, compressor pressure ratios. You have turbine entry temperatures. You have uh, basically for turbojet, these are the two design parameters. And also you have fuel air ratio, which you can increase or decrease based on your and also you will be able to design your components. All these things will be to do all these things. The basics is to understand the uh, the overall thermodynamic cycle. So people do the first thermodynamic cycle design, and that will be you will get most benefited from this course, especially those aspects.
Yeah. Yeah. Thank you, sir. Thank you
So
for that.
uh,
But
yeah,
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 yes, sir.
yeah,
Yes,
go
please,
ahead.
sir. Please.
Yeah, go ahead.
I mean, like, for me, yes, I got that. I mean, like, basically, most of the inputs will be taken from this thermodynamic analysis, whether it is pressure, what the
Hmm.
pressure is going to be in that certain area, like core,
Right,
in combustion or compressor, so that we will take that module and we will design it
correct.
again, applying this basic strength of material, whatever the two,
Right,
and doing some analysis part
right,
with a rough calculation, we'll apply them to the material level, right?
right, right.
Yes. Basically, I'm a design engineer, sir. That's it.
Okay,
I'm not much into this thermodynamics,
okay.
but I'm an aspirant. I want to get into this
Hmm.
aerospace engine.
Right,
So, yeah, that's in my mind. So that one day, the other day, maybe in future, after 10 years, I may work on this engine parts.
right, right.
That's in my mind.
So may I know your
Yeah.
present qualifications? Are you studying engineering or you have completed
You know,
engineering?
I have completed my engineering, sir, from Institute of Aeronautical Engineering
Oh,
as a
nice.
mechanical engineer. Yes,
Okay.
but I used to aspire those guys. Whenever
Hmm.
I see an engine or whenever I see their labs,
Right.
it's a fantasy for me. Then after I
Right.
started, I just trying to take advantage of this NPTEL and
Right. Right.
from you guys.
Yeah. Yeah. Sure. So, basically, what I would suggest is if you're asking for my suggestions, um,
Yeah.
uh, so there are different this is a basic understanding. You need to understand some basic idea of how these things works. So whenever you are trying to design, I know you are a design engineer, but
Yes, sir.
whenever you are trying to design, this is a fundamental concept. You should have some idea. Okay. Before
Hmm.
you even though you design, even though if you are doing a structural engineering, even though you are doing different things, um, this is some basic idea that you should have before getting into those advanced topics. Okay. And this course is very good in that way. Also what you can do is you can explore certain softwares if you are interested in.
Ah, yes, sir. Please.
You may no need to feel more intimidated by seeing these calculations, that we need to do a lot of calculation for each and every component. uh, if you're getting intimidated, you can also use some softwares. There are few softwares also. um, Maybe I can show you if you are interested. I will.
Yes, sir, definitely, sir.
Okay.
Actually, I even used to work on analysis also, sir.
Okay.
Yeah.
That's good. Then what I would do is I will try to present from my. Okay, give me a minute. I have a software named Para. I'm not sure whether you are aware of it. So let me show you that.
Okay, sir.
Okay. So now, were you able to see this parametric
Yes, sir.
cycle
Yes, sir. I'm
analysis for
able
gas
to.
turbine engine? So here you can I will show you how to get this software, but I will just quickly show
Okay.
you how to use this also. So this is like we have studied different turbojets, right? So you must have gone through weak contents, right?
Yeah, yes, sir.
Okay, so you must have known turbojets and turbofan engines, right?
Mm.
Right. So
Yes.
here you have but it's a preliminary level software. It's for for academic purposes, but there are few additional advanced softwares also like gas turbine. But you can start with this. So you have this turbojet and you have view data. Um, so in the view data, probably you are not seeing. 1 second. Give me a minute. So you are having this turbojet single spool data, right? So probably I'll drop this. So in this you also have this turbojet single spool data, which has like 1 point Mach number, altitude, temperature, pressure, CPC, gamma C. These are the things actually the input to our problems, for example. Okay, where pi's are nothing but your pressure ratios and polytropic efficiencies, component efficiency, all these things, and also finally you also give compressor ratio. So these are the inputs that you give, and if you just press perform calculations, it actually do the calculations for you, and then finally it will also give you the thrust. What is the effective thrust and specific impulse that you will be getting? Okay, sorry, here it is TSFC. Those are those things that you will be able. So for example, F by m dot, it's nothing but specific thrust. Similarly, you can also have uh, TSFC also. Okay, so these are the parameters that it actually automatically calculates for you. It's the same thing that we do. Um, um, so you'll be able to add mass flow rate here, and then the same thing that we do here. In addition, it will also give you efficiencies, thrust, and also somewhere TSFC also should be there. So fuel to air ratio is there. If you know fuel to air ratio, you can find TSFC also, right? So these things it will be able to give you. So you no need to go through all these calculations. So let's say when you are going into that field, uh, once you are starting to uh, yeah, once you are starting to design something, you can use such uh, yeah, so you can use such softwares like this, and then you will be able to uh, do the design. So I will also show you how to get it. Okay,
Okay, sir.
so were you able to see the software that I was
Yes,
showing?
sir. I'm able
Okay,
to see the screen, sir.
okay. So yeah, yeah, yeah. It's so you must know our one of the book I have here is this thing, elements of propulsion, gas turbine and rocket. So you can use this book. It's a so with this book they uh,
Yes, too.
elements of propulsion, gas turbines and rockets. So uh, actually this thing aerospace research central is there, right? So this website is has a lot of journal articles, also a lot of books.
Okay.
Okay, so let's say if you want to design aircraft engines, for everything they have books. Okay, uh, but some will be you need to purchase it. But for example, for this from this book you have the supplementary materials. With this supplementary material that is actually free to download from here. Here you can download this um, I think EPO2 software, right? This is what I was showing you. So this software
Okay.
does that It's a free software. You can download and install it in your laptop or computer. And this software will give you, let me open user guide. This software is the preliminary thing, turbojet calculation, turbofan calculations you can do. Okay.
Okay.
So this is one thing. Similarly, you also have a gas turb, but it is, you know,
Yeah, yeah,
proprietary
yes.
software. So you may need to purchase the uh, license for it. So that
Okay.
you can do when, let's say, you are joining some company like GE or something, they might already have. Uh, let's say when
Hmm.
you are joining that and when you are doing it, or let's say if you want to do your own startups at that time, you can, request for the licenses and do it. But uh, this actually this course will give you a initial objective of it. Okay.
Yeah.
So
Yes, sir.
yeah, so in that way, it is better that you follow this course and get some initial idea about how are things. What is the also we will be also showing you what are the recent advancements and the future progress of these gas turbine engines. Even though for the first 4 or 5 weeks we were reading about each and every engine. We also introduce its thermodynamic concepts, but also we will be sharing like what is the present engines, what are the engines capabilities, and whatever we solve in each of these questions also like more real life scenario questions basically.
Yeah.
So in that
Like
way,
industrial, I mean, like whatever the industries are doing, I mean,
right,
like what is the industrial practice is what we require, sir.
right,
Because study is different. I mean, like lectures, all these are different from industrial practice. I know that much.
right,
Since I'm working for 3 years,
okay,
I know that much.
hmm,
In industrial practice, a design scenario is a complete different thing,
right,
where we use tools, analysis, and like the standards what they use is completely different and can't be found outside.
right, right,
Not yeah, even in engineering also.
right,
Even when I did engineering, it's not, I mean I can't apply whatever the knowledge I have in engineering. It's
hmm,
completely different thing in real life scenario right now
right,
for me.
right, right, right.
Yeah.
So it is true. It is true.
So when we get if we get an example, I mean like you were saying about GE, right, sir?
Mm-hmm.
If we get a live example, like a bit of what they do exactly, what the I mean like what will the problem solving they do? I mean it will be very helpful and it will give a different view.
Okay.
I'm expecting that,
Okay. So,
you
um,
know.
yeah. Um, hmm. So
I know
maybe I
it's a
will.
little
Yeah,
tough,
yeah.
but
Actually,
yeah.
I will contact professor and I will let him know that uh, your interest. So um, let's see whether he can. But although this does not directly apply from our course, it is not directly the
Yeah.
aim of this course. But I can ask him some papers or something which you can read for the designing of this, how the industry
Yes.
actually does those things I can share. Yeah. So
I mean, like
are you working in
yes, sir.
aerospace industries or currently you're
No, sir, no,
no?
sir. I will make a naval, our submarine department. So,
Okay.
special purpose was
Okay. Okay.
for defense.
Okay, okay. So, yeah, I can share with him if it's available from his side or some documents or something which would be helpful for you. I will share it with you. Okay.
Okay, sir.
And so, yeah, so in that way, I also recommend you to check this website. It's actually, let's say, for example, let me search also for you. Um,
Okay, sir.
So these books are not written by the academic people. These are written by the industry people who made aircraft engines. Okay, so you can check aircraft engine design. Yeah. So yeah, these things you can check actually. These books would be a very helpful for you. For example, this book, Aircraft Engine Design. Okay, I think there is a new thing also came. Third edition was also there. Uh, you can either purchase or different ways of downloading a book. um, Aircraft engine design, third edition. Yeah, this book. So this book will be, they will give you the uh, real design process. It's actually, let's say, let's see. Hmm. So you can look at the authors and who are they. So these people are actually, they have full experience in aircraft propulsion for like 50, 60 years. They worked with industries. They have continuously collaborated with them in developing important engines and aircrafts throughout the history. It even starts from 1950s. Okay, so uh, this, I think this book you can have a look. And also, but the basic book was this one which I was telling, the elements of propulsion, gas turbines and rockets. That's a basic
Yeah,
book
yeah,
which gives
rockets.
you, so it's like, you can think of it like this. In the mechanical engineering course, you first starts with thermodynamics, fluid mechanics, but without knowing that concepts, if you go into, let's say, a CFD industry, and if you want to do CFD analysis, you will not be able to do, without understanding fluid mechanics, right? So which means this fluid mechanics and thermodynamics is like a fundamental subject which you may need to know, let's say if you're doing a CFD research. Similarly, if you are doing an aircraft, design, engine design, like let's say for structural engineering, you have to do something like strength of materials. You need to know. When they say stress, what does it mean? When they say strain, what does it mean? So these fundamental concepts you will be knowing, right? Similarly for
Yes, sir.
aircrafts, similarly for aircraft engine designers, things like that, the fundamental concepts which you may need to know are the terms that they use, the fundamental relations that you encounter during design. All these things will be given by both by this course and also the books that we refer in this course. So
Okay.
here is where you start, even though it may not directly apply to your design process. First you will start here, and then you will read advanced books, something like this, aircraft engine design. Okay, it's a bit advanced from whatever we are all, and also it is bit out of topic from whatever we are talking in this course. Okay.
Hmm. Yeah,
Mm,
thank you for that, sir. And
okay.
and
Yeah.
also I have a see, sir. I mean, okay, sir. Consider an ideal situation that we learn all this stuff, and yeah, yes, and we are able to design an aircraft.
Mm-hmm.
So, in industry, uh, for us, consider we are a design. We design something, sir. I
Okay.
mean, like we design a wall,
Mm-hmm.
and it has to meet some standards,
Right, right, right,
right?
right.
Whatever the ISO standard, IS standards, or
Mm-hmm.
civil aviation standards. So it will be very helpful if for us we consider me starting a startup, and I
Mm-hmm.
say I can supply a module for a company, and I
Mm-hmm.
have to be certified that this module will work, no, sir.
Right, right,
So
right, right.
what are the certifications that really require in real industrial practice?
I
Uh,
see.
it will be very helpful, sir.
Okay. Um,
Yeah.
yeah, I am actually not aware of those things. Uh, Maybe I will ask Professor if he is aware. I will share it with you,
I
and
mean,
also I will look
maybe
into
it's
it.
out of the question,
Yeah, yeah, yeah. I
but
understand that.
I think you people are the persons in the best minds in the world, and I consider that you will get the answer.
So,
Yeah.
yeah,
Even Google also not giving these proper answers, sir. That's why even I do ChatGPT or whatever the things.
right,
I won't be able to get the standards. What say I use the standard 447. Like if I say circuit standards, what are the standards for fasteners? I will get no, sir.
right, right, right,
But for the aero standards, I can't search for the aero standards. What are the standards? And if you give, if you guys at least tell the what are the standards numbers, like
mm-hmm.
ISO this one or
Mm-hmm.
ASME, it will be very helpful for us to
For
design or to consider. Yeah.
design of aircraft engines.
Yes.
Okay.
Yes. Yes.
So yeah, I will talk with Professor. Um,
Like,
so what
like,
actually what you can
mm,
get is, probably you can end up getting, compressor blade design standards. Probably
yes.
uh,
Mm,
you, component standards you might be able to find out. Um,
Yes, yes.
let's say turbine blade. Actually, these are very advanced designs, and people don't usually put it uh, for common people actually.
Yes, 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 sir.
So
Me.
turbine blade design standards. Yeah, I understand what you are telling. So yeah, there might be something. So requirements to ensure engine integrity, wind turbine. So wind turbine blades you will have, but not the gas turbine blade. So the reason is
Yeah,
yeah,
it's done by R&D and they won't be publishing outside. Yeah. They
no,
won't make
yeah,
it outsource.
yeah.
Yeah,
If it's an
open
open
source.
source, they
Yeah,
cannot make this open source because they want it to be you know secret.
yeah.
They want to have every country, they want to have good aircrafts, and good aircraft comes from aircraft engine, and based on the current knowledge that you must have gained from this course,
Mm.
it all depends upon how high you can go at the turbine, right? The turbine entry temperature should be high, and there are different ways, different lot of research is going on to improve the thermal and mechanical load that a turbine blade can handle. And if you're there, people are continuously trying to increase it, and if they increase it, if they achieve some breakthrough, they will not publish it. They want their country to you know go up.
It's $1 million research. How they're
Right, right.
going to distribute?
So they won't be able to do open source, but
Yeah.
some things will be open source. For example, uh, there might be some engine designs would be open source. Something, what are the variables that they use? Those things would be open source. Using that only, you may need to you know try to connect the dots. But
Mm.
turbine and its standards you may not find also. There is also
Yeah.
high possibility that you will not find. And but industry standards, what they do is something I can try. I will ask professor and I will get back to you. Okay.
Oh, that's good.
Okay. I will see
And
how much we can get out of it, and I will give it to you.
I mean, like, and also, sir, my question,
Mm-hmm.
not only not only for designing,
Mm-hmm.
for say we design an engine,
Mm-hmm.
okay, it's an ideal situation. We won't be designing it, but consider, okay, we finally designed it and we are able to manufacture it.
Mm-hmm.
Uh, okay, and what should be the certification that required from point of Indian point of, I mean, general civil aviation?
Right.
There will be board, no, sir,
Mm-hmm. Mm-hmm.
and
So
they will certify those engines, right?
right.
For whatever the application. Yeah,
Mm-hmm. So
I
actually,
mean, like, mm,
yeah, that is true. Uh,
because many of the startup people, even though they want to invest or even they want to think about it, they end up at this point, no, sir.
mm-hmm. So actually, in terms of design, for example, let's say if you consider this course, okay, in let's say if you came up with a design of Aeroengine, something which is something novel, and you wanted to do some patents or something like that. First thing they will see is the emission norms. That is very clear, right? So there will be some if you come up with an engine, let's say if you use different fuels, what is the NOx emissions? Because people are going towards the net zero emission, right?
Yes.
2030.
Yeah.
So that is something would
Mm.
be very important. And also people will be looking for reliability, uh, uh, how much life of your engine, all these things will come into picture. Those, you are right, those certifications that we need to do to get the engine out, right? And
Yeah.
till now probably there are only few startups who are doing. Probably some IIT Madras incubation centers might have some startups, Probably IIT KGP also might have. Uh, but what they do is they do for a small engines. It's a small gas turbine engines or micro gas turbine engines. It's not really to an extent of running an aircraft. Okay,
Yeah,
uh,
yeah.
running an aircraft, let's say military aircraft. DRDO is trying to develop Kaveri engine, but they are the
Yes.
only one in India. They are trying it for a military aircraft. If my uh, Yeah, so as far as I know, so in terms of certifications, getting an if lot of people are doing it, then we will have some good idea about it, how it is happening.
Yes, yes.
But only less people are doing it, and also one or
Yeah.
two is doing it. So yeah, it is very difficult to get those things out. Right. So yeah, I will ask about this also, the certification standards. If you want to design, what is the design standards that in industry people usually follow? And also if you want to get it out, what is the certifications that you need to go through? All these things I will ask the professor, and if he knows, I will share it with you.
Thank you, sir. Thank you very much. Thank you for that.
Okay. All right, Matesh, no problem. Yeah. Okay. So currently you are employed in which industry?
So I am working in a company called Vertex, sir.
Okay, okay.
They design like submarine oriented walls,
Oh, I see.
special purpose walls, yeah, for
I see.
DME, so like that.
Okay. Nice. So you want to change? Do you want to try
Yeah.
aircraft aero
Yes,
engineering?
yes, that's
Yeah. Sure.
that is my fantasy, sir. Whatever,
Okay.
yeah, aspiration for that. So
Yeah, yeah, yeah. All the best. Stay on track. You'll be able to reach, I guess.
thank you, sir.
I will
Thank you,
get
sir.
back to
And
you. Yeah, yeah. I will get back to you next week. Okay.
yeah, thank you, sir.
All right. Bye, bye.
Bye, sir.
Okay. This is done. Burner efficiency. If okay, okay, and not if